Hello, good afternoon, and welcome to a new online event within the European Meteorological Society webinar series. In this occasion, we present a topic which is very relevant, not only scientifically speaking, but also from the communication point of view. The topic is to estimate how human influence has changed and is changing the likelihood and severity of recent extreme events, and do it quickly, both things. Before introducing our speakers today, let me recall some practical hints. The webinar is being recorded and will be published later on the EMS YouTube channel. Please, for the questions, use the chat during and after the presentation. The questions will be answered, all of them, at the end. Vesna Juricic will organize, group, and read the questions on the chat. Finally, send suggestions of topics and speakers to us. Whatever topic you consider could be of general interest or attractive, I'm sure it could fit in this format. And now let me introduce you to our speakers, to our presenters today. Friederike Otto is a senior lecturer at the Center for Environmental Policy of Imperial College in London. She has co-founded and currently leads the World Weather Attribution Initiative, which is an international effort to analyze and communicate the influence of climate change on extreme weather events. The second speaker today is Ben Clarke, who is a research associate at the same Center for Environmental Policy. He has developed a protocol for rapid attribution of tropical cyclones, and he will show us some example today in collaboration with colleagues at the Grantham Institute and Climate Central. Please welcome to this event today, and thanks for your collaboration. Go ahead with your talk, which is titled Rapidly Attributing Extreme Weather Events to Climate Change. Go ahead, please.
Yeah, thank you very much. And I will just quickly share.
Perfect.
Good, sorry. Okay, so as Ernesto has said in the introduction, I'm leading an initiative called World Weather Attribution, and Ben and many others around the world are working on this team. And we are scientists, and that includes just physical scientists, climate scientists, but also experts on vulnerability and exposure, so social scientists. And we are aiming to answer the question, what is the role of climate change in the immediate aftermath of an extreme weather event occurring, but also looking at what else has happened and what led to a weather event turning into a disaster, so vulnerability and exposure. So in effect, what we are aiming to do is to identify in our area of loss and damage that we are living in, the experiences that we have with the relatively abstract science of climate change. And I will very briefly introduce the basic idea of the method that we're using, and then Ben will give a more detailed example of how that looks like in a more challenging type of extreme event. So I will use an example of extreme heat for two reasons. One reason, and that's what I've tried to illustrate here, is that we have a huge number of extreme heat waves and heat waves that are so hot that they would basically have been impossible to occur without human-induced climate change around the world. But so it's the type of extreme event where climate change has one of the largest impacts, if not the largest, but also extreme events, extreme heat is often still underestimated. And in many parts of the world, there are actually no forecasts for heat waves, and heat waves are not reported or recorded. And so that also means that there's no early warning, no early action, despite heat waves being extremely deadly. And this is just to give you a flavor of the kind of findings that some of our studies have in heat waves. I don't expect you to be able to read these, but really just to show they happen everywhere. And all the pink ones here are heat waves that are so hot that they would not have occurred without human-induced climate change. And how do we know this? So to give an example of a heat wave that you probably have not heard about, which is a heat event that happened in October 2023 in Madagascar. And you can see Madagascar over the 7 hottest days in that October on the right-hand side on the map. And you can see that it was the anomalies of temperature were very high everywhere, but particularly high in the eastern part, which is the mountainous part, and where also the capital of Antananarivo is. And to now answer the question what the role of climate change is, the very first step that we have to do in every attribution study is to find out how do we actually characterize this event. And in this case, we, with a heat wave, and especially a heat wave that basically held for a whole month, that was relatively straightforward because one of the definitions of the heat wave we used was just the month of October, so average temperatures for the month of October. And in the published study, we then also looked at alternatives, but just because it's simple, I'm using this one here. So after we found out how we characterize the event, so average temperatures in October, the next step in the attribution study is then to find out in today's climate, in the world that we live in today, or that we lived in October 2023, which was at the time about 1.2 degrees warmer than it would have been without human-induced climate change. What kind of event is this? And to do that, we need to simulate possible weather, so possible October temperatures in Madagascar, in the world we live in today. And that's what you see in the middle here with the red curve. And we use observations and statistical modeling, but also climate models to simulate possible weather in the world we live in today. And in the illustration on the left-hand side, you can then see the result of this in this middle square, which has the one pink dot inside, because when we look at all the possible October temperatures in today's world, we find that the observed event in 2023 was about a 1 in 100-year event. To now, once we've done that, do the actual attribution step, we need to do the same thing, but for the world that might have been without human-induced climate change. So we're a 1.2 degree cooler world. And again, we can use observations and scale them as if they had happened in a world without human-induced climate change, so in a 1.2 degree cooler world, using statistical modeling. And that's what you can see here, what the result that you can see here, that's just scaled down observations. But we also use climate models to do that. And when you look at the blue curve that you see here, that shows all the possible October temperatures in a 1.2 degree cooler world, you see that the actual event that we have observed in 2023 is nowhere to be found on this curve. And that means that the temperatures as hot as they were observed in October 2023 would have been impossible without human-induced climate change. And that's what's illustrated with the just gray dots that you can see here on the leftmost square. And of course, we can't do this just for the past, but we can use the same method and then ask, and what will be possible October temperatures in Madagascar in a warmer world, so in a world that has maybe 2 degrees warming. And in this case, we found that this event would then be about a 1 in 5 year event. But of course, this heat wave, as we've characterized it here as the average October temperatures, is one way of characterizing the heat wave, and that it wouldn't, so October temperatures of above 25 degrees or about 25 degrees on average would have been impossible without climate change. But that doesn't mean there would not have been a heat wave. So we can also ask the question slightly differently and not say, how has the likelihood of this event changed? But we can also say, given the likelihood of the event, how has the intensity changed? And this is what is illustrated here with these burning stacks, or however you want to call that. So in the middle, we have the event as it is today, so or in October 2023, October temperatures over Madagascar of about 25 degrees on average. And that's the 1 in 100 year event today. And on the left of that, you can see how hot a 1 in 100 year event would have been in a world without human-induced climate change. And you can see that it's about 23.5 degrees. And so then we can say that climate change made this event 1.5 degrees hotter. And of course, again, we can do this for the future, where you see that the intensity would increase by another degree approximately. So this is really the basic methodology. And this is a bit of a schematic way of showing it. In reality, we always look at return time plots, which I just show here because I'm sure Ben will have lots of these, so that you've seen them once, where we have, it's the same thing as the probability curves that you've just seen, only that we have on the y-axis the temperature in this case. So this is the same data, just shown in a different way than you've seen in the curves before. And the blue crosses here are October temperatures as they might have been in a world without climate change. And you have on the x-axis the return period, where you can see the cross here where the pink line is of the event that we have observed. And you can see here that the blue line never crosses the pink line. So this is in essence, at least the idea of what we do in every attribution study. We usually do that with several different observational data sets and also with several different climate models, so that the interpretation of the results is not always as straightforward as in this case. But then, crucially, the other important aspect of every attribution study that we do is to look at what caused the damages, why were the events impactful. And there, what you see in the schematic here is really just an illustration where it's not expected that you can read it or see every little drawing, but just to see how many types of impacts there are from an extreme heat event on health, on livability, on critical infrastructure, on economy, agriculture, water, and the environment. And of course, these impacts, so if you have agricultural losses, that of course is not just an agricultural impact, but it affects economy, food prices, and that then has effects on health and on livability. And so all these factors are really important in driving what actually the impacts of a heat extreme are. And to understand them a bit more, to understand which are the biggest drivers, and also to inform what would be the most important things to do with respect to adaptation, we look at the different factors determining them. So for example, the institutional ones, was there early warning? Were there early action? Do people know what to do with the early warnings? Then the physical ones is just, are people living in informal housing? Is there a housing code? Do people adhere to the code? What's the sanitary standard? Then a really important one is the attitudinal one. If people are unaware of the dangers of heat, or just think it doesn't, because maybe they are not elderly, they think it doesn't affect them, then they would not necessarily do what is needed to do for early action. And then the more standard drivers of vulnerability, like social just levels of education and economic drivers. And all these factors play a huge role in what the impacts of the event are. Just to give one example, a storm that happened here in the Mediterranean a couple of years ago, Storm Daniel, the same storm killed 17 people in Greece, but over 4,000 people in Libya. And so the difference was the infrastructure, the vulnerability, and exposure. And this is often much more similar depending on the extreme event, but of course there are factors that are specific for extreme heat and others for flooding. But what we always find is that early warning is really, whether there's early warning that is linked to early action, is really what determines whether there's a high or a low death toll in extreme events. So this was really a very brief introduction of how we do attribution, or what's the idea behind it. And of course, we can't do this just for heat waves. So this is just an overview of the studies we have done in 2024, where the pink dots show events that we studied across the world where we did find the role of climate change, where the white ones, well, if you look closely, you can see two. We found that climate change did not actually affect the likelihood and intensity of the event. And there's one that we did last year that was inconclusive. And we've just published, or we are about to publish tomorrow, another one where we had the same result, that just with the available data, we just couldn't say. But I will hand over to Ben now to talk you a bit more into detail of what this means in practice, rather than in this very simple, almost theoretical example that I've shown here.
It's ready. Let me just share, see how that goes. Okay, does that look okay?
Yes.
Cool, good. Yeah, so hi everyone. Thanks Freddie for the introduction, and thanks everyone for joining today. So I just want to talk about tackling specifically the rapid attribution of tropical cyclones. This is a relatively new thing for our team. So to do so, I'll talk a little bit about just our understanding of changing extremes generally, then why this has been one of the thornier challenges, what are the difficulties around rapidly attributing tropical cyclones, and then hopefully we spend most of the time talking through a case study so you can see this in practice. So these maps are from the IPCC AR6 report. So in the center, this is heat waves, bottom left is heavy precip events, and bottom right is drought. So this is essentially observed changes in that type of extreme in different regions of the world, and the color illustrates essentially whether there's an observed change or not and the direction of that change, and then the dots indicate a level of confidence with which that can be attributed to climate change. So essentially the point of showing these maps is just to say that our knowledge of different extremes and how they're related to climate change varies very strongly by the type of extreme and by the region of the world. So within that picture, tropical cyclones are essentially no exception, and really they are actually some of the kind of most destructive events that we see anywhere in the world, and yet our knowledge is still quite lacking. So this just is just a table to illustrate that. So you can see essentially a list of major tropical cyclone events within living memory, and most within very recent memory, along with their death tolls and damages. Some of the deadliest events that have been experienced in recent years have been tropical cyclones in the North Indian Ocean, so affecting areas of South Asia, Southeast Asia, where there is high population density and high vulnerability. As Freddie alluded to, those factors can make a real difference on how these events affect different areas. Meanwhile, hurricanes, so from Katrina to Harvey, which you'll all have heard of, are some of the most damaging in terms of raw destruction of assets and wealth, around the world. And of course, again, that's related to the fact that wealth is higher in given places and so is more exposed. And a given amount of wealth loss might mean different things to different places. But nonetheless, these events get a huge amount of attention. And what that can mean is when these events get attention, people ask the question of how has climate change played a role in this event? And particularly, there can be a tendency to just say this event is because of climate change. And while that is the case for potentially some heat waves, as Freddie has shown, that's not always exactly true. And it's important that these major events are attributed accurately to build up kind of a clear picture on where climate change is and is not playing a role, so that A, we build trust when we do make a statement about these events, and B, for just preparing for risks kind of now and in the future. So some of the main challenges around attributing tropical cyclones. Firstly, these are very complex and compound events. So what I mean by that is there are many mechanisms through which climate change can affect the frequency and intensity of tropical cyclones. So whether that's through sea surface temperatures or atmospheric stability or a range of other factors that can affect where they form and how long they last and where they strike. But also the ways in which tropical cyclones affect societies is through multiple different mechanisms. So, for instance, rainfall, high winds, and storm surges, all of which can be affected by climate change in different ways. There's also variation in the nature of these events by different ocean basins. So changes due to climate change will be different in different places potentially. So from the North Atlantic, you might have different changes to the North Indian Ocean, to the Western North Pacific. So it's important to study events as and when they occur. These events and kind of the strength of cyclone seasons can be affected by internal variability, again, in different basins in different ways. So we might have to account for things like ENSO or other drivers when we do these studies. And finally, when we conduct rapid attribution studies, we have a very short timeline. That means we are accessing kind of already run model data. Highest resolution we're able to access quickly is generally on the order of kind of 25 kilometers, which is much too large to explicitly simulate the highest category of storm, at least in terms of like the physical mechanisms that generate the really high winds from those kinds of events. So to kind of bring this together, our idea was to use our traditional approach where we can for the aspects of the events that we can study, and then to bring in other recent approaches developed by colleagues to study different aspects of the event and see if we could bring together one kind of coherent picture. So we can talk about Hurricane Helene as a case study. This had kind of very severe impacts in the US. It was the deadliest event in the mainland US since Katrina. It also actually flooded the NCEI, which is an institution that stores information about the most destructive weather disasters that have affected the US and around the world. So there was a lot of media attention around that particularly. So there were several aspects of this event that we wanted to look at, as I've mentioned. So firstly, just to talk through what we did in regards to rainfall. This is similar to what Freddie's already shown around heat. But I'll just talk a bit how we made decisions with respect to that. So what we have to do, as Freddie has described, is characterize our event. So we look first at what happened. From this, cyclone. So we know that Helene formed in September, so this is within the tropical cyclone season, so what we'd expect. Here is the track. It kind of traversed the Gulf of Mexico, which was unusually hot at the time, made landfall in the panhandle of Florida. It brought extreme rainfall to a coastal region, and then tracked inland, interacting with a frontal system that was already quite active, to also unleash a huge amount of rainfall in this region of the southern Appalachians, which resulted in really extreme flooding. So we decided to look at the rainfall in these two separate regions, partly because they have different climatologies. So then we could kind of quantify them separately rather than looking at one sort of amorphous blob from the storm. This was advised to us by local scientists who were kind of aware of the issues in different parts of the states. So once we've identified those regions of interest where we're looking at changes over time, we can calculate time series. So we looked at the 3-day annual maximum rainfall in that northern region I showed, and the 2-day annual maximum in the southern region. This is in a series of observational and reanalysis gridded data sets. So that's the first part of our analysis. And once we have these time series, we can fit statistical models. So to each time series, we fit a non-stationary GeV in this case, and we assume rainfall will scale with GMST, which we fit as a covariate. And once we have a model that looks something like this, we can evaluate the likelihood of an event like Helene at each level of our covariate, so the modern climate and a much cooler pre-industrial climate. So this just shows the for one of these observed time series. So we see the pink line represents the rainfall of Helene, and we see the return period here in the present climate was somewhere close to 100 years, whereas in a pre-industrial climate it would have been several hundred years, or equivalent intensity of an event of that likelihood has changed by some tens of millimeters. So we do this for all our observational time series, and then we repeat the same analysis for climate models. So ideally several ensembles of climate models, and then we synthesize the results. So in this case, we used Cordex and GFDL models at 25-kilometer resolution. So the synthesis looks something like this. Here we have in blue the observational data sets with their best estimates and intervals representing the uncertainty ranges. We synthesize those into a single estimate, and then the same for the climate models, which are synthesized, and then both observations and models are synthesized into a final synthesis result. So that gives us a probability ratio for an event like Helene and a change in intensity for an event like Helene. And as Freddie also said, we do this both for the present with respect to the past and some future warming level with respect to the present using just climate models. So I'll cover all the results at the end. Okay, so the second aspect of the storm we wanted to study was the kind of wider environmental conditions in which the storm formed. So this is taking a step back from the impacts to just look at, were the conditions conducive to this kind of event, and how are those conditions changing? So Freddie, can you see this list, the row of videos of everyone's faces on your screen as I share the presentation?
Yes.
And I keep moving it around.
You froze occasionally, but only very briefly. So it's okay.
There's something I don't know whether I keep moving it around for everyone or not.
No, it's fine.
Okay, cool. It's fine. Sorry, I just had to ask because it was really bothering me. So back to the potential intensity. So this is a quantity that describes the theoretical maximum intensity for a given storm. So it's dependent on various properties of the ocean and the atmosphere. So SSTs, the temperature and humidity profiles, and the sea level pressure. So on the right, you can see a map here of, again, the track of Helene. And the grey area is the area in which we considered essentially around the track relevant for the formation of the storm. And you can see the map of values of this quantity Vmax, which is the theoretical maximum intensity. So we use a similar approach to what I just described for rainfall, but model changes in this potential intensity region, and again combine reanalysis data, this case ERA 5 and CMIP6 models, to look at changes over time. We find a really quite strong, robust trend in potential intensity. And when you look at the synthesis, again, you can see that. So a change in intensity on the left here, 0 obviously represents no change. And you can see the synthesis result is significantly above 0. And again, the probability ratio is largely all above 1. I'll list all the results at the end, but yes, just the wider message is we use the World Weather Attribution Protocol again for potential intensity. So that's one way of looking at the environmental conditions. We then looked at a second way, which was just at the sea surface temperatures using the climate shift index. So this is something developed by colleagues at Climate Central. So essentially, this is they have a tool both for the land and for the ocean. They're separate but use essentially the same method. This is essentially a pre-computed kind of grid by grid cell method at which, so you can essentially take observed temperatures and compare pre-computed distributions of temperatures at the same time of the year in the current climate versus a pre-industrial climate, and you can do this live. So this is very similar to the World Weather Attribution method, but on a pre-computed grid. And for their ocean data, they use OISSTs and CMIP6. And the reason we use this in addition to the previous method was because since this is on a grid and also at sub-daily scales, they're able to essentially take every point along the storm track and look at the exact conditions experienced by this particular storm, and then assess the change in likelihood and intensity of the SSTs which fueled this storm. So when we do that, we get these curves. So the red dashed line here represents hurricane intensity over time. So you see reach tropical storm status sometime on the 24th of September, to hurricane status a day and a half later, and then peak intensity at landfall on the 27th. And over the course of that time, on this top blue curve shows the increase in intensity due to anthropogenic warming. So we can see from the axis, essentially the SSTs were always at least a degree warmer than they would have been without climate change. And similarly, the bottom blue curve shows an increase in likelihood of those SSTs. So again, the scale here is much larger, so a factor of 100 almost always above pre-industrial climate, and actually peaking at an increase in likelihood of 500 around the time the storm reached tropical storm status. So those two together give us quite a clear picture of how the environmental conditions that fueled Helene are changing. And in particular, it's useful to both have potential intensity and then to disentangle that a little bit by just looking at sea surface temperatures along the track. And then the final aspect of the storm we studied was the wind speed. So as I mentioned, this is very challenging from a modeling perspective. But the IRIS model developed at Imperial College and the Grantham Institute is a stochastic model of storm tracks and intensities. So it removes the need to explicitly model these events individually. So this is essentially a decay-based model. So it takes observe storm tracks from the IBTrACS database. It takes them at the point of lifetime maximum intensity, and then it essentially stochastically perturbs the decay rate and the direction of the track to then eventually find a landfall intensity and location. So you can run this over and over many times and get many thousands of years of these synthetic tracks. And the way the IRIS system deals with creating current versus pre-industrial conditions is using a change in zonal mean potential intensity. So this is an observed change in how the potential intensity has changed over time. So you can see some areas has increased a lot, and some areas less so, but this axis goes from 0 upwards. So essentially, potential intensity has increased everywhere in at least this part of the ocean. So when we create these synthetic tracks, we get like a huge number of landfalling intensities, and we can use that to study specific storms. So in the case of Helene, we picked one point where Helene made landfall and then considered an area within 2 degrees as similar to that storm. And these points all represent individual data points in the database, essentially. So from those, we can build return curves of how events that make landfall in a similar area are changing with climate change. So that gives us a return curve very similar to our previous methods. So the blue curve is the pre-industrial return curve for this area, and orange the 2024 conditions. So when we look at an event of Helene's magnitude, which I think was about category 4, we find that the return period has gone from about a 1 in 50 year event to about, from a 1 in 130 year event to about a 1 in 50 year event. So that's a probability ratio of about 2.5, and equivalently is increased in intensity by about 6 meters per second. So that, as a roughly 10% shift, is quite a lot when the damage of these peak wind speeds quite heavily dependent on, I think there's a roughly cubic relation around the category 4 region between magnitude and damage from these storms. So just to summarize briefly, we had a situation where just our methods alone were not up to the job of rapidly attributing tropical cyclones. We addressed this by bringing together different approaches and looking at lots of different variables to kind of build up a more comprehensive picture of tropical cyclones. And when we look at the results from this case, from Hurricane Helene, we found consistent increases across every metric we looked at, from rainfall, potential intensity, SSTs along the track, and the wind speeds, both in present and in future. So that gives us a very high confidence view that this storm in particular, and storms in the region, are becoming more intense and frequent due to climate change. And that was everything.
Okay, thank you both for your talks, your clarifying talks, and now we'll pass to the questions. Please write your questions on the chat, please.
We already have one.
Okay.
So Mark Broholm write the question: has any attribution study been conducted regarding the heavy rainfall event in Valencia, Spain last autumn? Which are the main headlines? These events tend to be more frequent or just more intense in the next decades? So who will answer?
I can start. So we didn't do a full attribution study in this case, but we looked at just observations. So we essentially did a trend detection on events like the one that hit Valencia, and I think we found a fairly strong increase in events like that that have been observed. The challenge, however, was that this was a quite intense sub-daily scale event. So our data was only daily, which means we aren't necessarily capturing the full intensity of the event. And also on the timelines we work on, again, getting sub-daily data from models is very challenging. So we didn't do a full attribution study on that one.
Okay. Ernesto is asking, will in the near future this service of rapid attribution be part of the Copernicus portfolio of services? How will the protocol be then for selecting the extreme events to be analyzed? Who will have the initiative for proposing cases?
I can maybe answer that because I can then answer much better also the question that Sergey Gonzalez put in the chat. So there is indeed in the plan to do rapid attribution studies as part of Copernicus, and there was a pilot project that had been concluded with also people who were involved in world weather attribution a couple of years ago, and now there is a new project that has just started in March to actually implement it, and it's based on the methods that we are also using in world weather attribution. And I don't know how in the Copernicus version the decision will be made which events to study, but I can answer the question of how we decide which events to study, because we work with the Red Cross Climate Center and we have developed what we call a trigger methodology that is based on humanitarian impacts. So for each type of extreme event, we have different criteria. So for example, for floods, the criteria that there are 100 or more deaths, or 1 million or more people affected, or 50% or more of the population affected, or there is a declaration of a state of emergency on a national level. And yeah, for storms and droughts, the criteria are relatively similar. For heat waves, it's more difficult. There, it's really much more based on actually the forecast and the potential to affect people. So if they are happening in highly and densely populated areas, because most heat waves are just not monitored so that we wouldn't have the data. And then, so every Friday we have a meeting where we discuss all the events that have been triggered. And I think, yeah, we had 12 as the maximum this year, but usually it's something between 3 and 8 events, and then depending on the availability of people power in our team, but also whether events are happening in a region that is understudied, we then make a decision where we do a study. And so we deliberately try and study events that happen in regions that have had very few studies. But because the media is much less interested in these, you hear more about the ones we do in the Western world.
Thank you. Eddie Graham asked, how are artificial intelligence models doing at simulating very extreme events, those not possible in previous climates, given that IA is trained on historical data?
Ben, do you want to say something?
I can. I'm not. I don't particularly use any AI, and we haven't really interacted with any AI-based data so far. So I couldn't say confidently. It's a really good point. I know that, for instance, you would have, if you wanted to, I guess, train AI on future climates to find what the most dangerous events are, you would be reliant on climate models to also predict these kinds of events, and quite often they do underestimate the trends in extremes we see, or aren't able to capture the most extreme magnitudes of events anyway. So I think even before AI has that challenge, I think a lot of climate models have that challenge as well.
Okay, thank you. Philip Bukowski asked, I wonder what is the context of the attribution? In which cases is this done? Working more on the side of on the side of impacts and the communication myself, there is usually plenty of media buzz connecting extreme events and climate change. I vividly remember the flooding in East Europe last year, while around 30 years before there was a millennial flood that in fact was less extreme than this in 2024. There was a joke that millennium floods are happening every 30 years now. What are your comments?
Well, actually, from a weather point of view, we have done a study on that event, and at least for the event that we looked at, which of course the exact numbers depend always on how exactly you define the event. We did find that it was still a rare event, but what we also found, and what I think is the big difference here, is that the death toll was much, much lower than in the earlier floods in the same region that happened in 2002 and 1997, even though from a rainfall point of view, this event was actually worse. And so that actually shows that there has been investment in early warning, and particularly early action, so that that people could evacuate, could go to safety. The economic damages were still quite dramatic.
Okay. Bernard Jimenez asked, do you get different results for tropical cyclone attribution depending on the resolution of the climate models employed for attribution?
Well, that's certainly part of the reason we don't do any attribution of the wind speeds with the climate models at all, because then certainly yes. It's also the reason we only use the highest resolution models we have access to. So we only use 25-kilometer resolution models. I think coarser GCMs would get different results. There are studies also showing that, you know, even for rainfall, the smaller, you can go to smaller resolutions and they then pick up the very intense rainfall that you get close to the center of the storm. So for those really localized extremes, you would need higher resolution models. But for the scale, like the resolution of model we use is able to capture the scale of rainfall we're looking at. We're generally looking at a fairly large area. To look at a large area with the GCM, I think you would also get different results though.
Okay, Jose Prieto asked, what is the point of a rapid attribution as opposed to a sound, deep, or reflective attribution to the current climate? Where is the urgency?
That's a bit insulting, I would say. It's not necessary. If you don't like what we do, you can just ignore it, but you will find that the methods that we use are exactly the same that are used in sound, deep, reflective attribution that are peer-reviewed. It is just that the results of these are only available a year or two after the event has occurred. And when extreme weather events happened, as was also just mentioned, there's always a question in the media, but also by decision makers, on what the role of climate change is. And for the longest time, everyone had an opinion on that, but the scientific community was silent. And to change that, we founded World Weather Attribution to provide scientific evidence based on peer-reviewed methods in the time frame when these public discussions happen. And that's where the urgency is, because there is a relatively small window of opportunity. So even if you don't want to hit the media, if you just want to advise people who are thinking about rebuilding, relocating, adaptation, there is a window of opportunity of a couple of months after the event occurs when these decisions are made. And so having scientific evidence available in that time frame has been shown also by lots of work that has been done with the Red Cross to be really important.
Thank you. Diego Campos, thanks for the presentation, and he said it was very interesting. What would be your recommendation for using coarse resolution GSMs on weather systems like hurricanes or cutoff lows?
I think just similar to my previous answer, I would not. I don't think we ever would use the CMIP resolution models without any downscaling on that kind of system. We generally go to at least regional climate models.
And Sergi Gonzalez asked, do you have more challenges in complex terrain regions due to model resolution?
Yes, the simple answer is yes. We will try to avoid situations with complex terrain very often, but it's not always easy to navigate, and sometimes it means we can't study a certain event.
And Matthias Lang asked, how will you develop your methods further? What are the next steps?
So I think one of the important next steps is, I think someone shared a Klimameter link in the chat earlier. So Klimameter is not doing attribution, but what they are looking is they look at analogs. So in the look at what's the state of the atmospheric circulation, and then see in the past has there been a change in the number of these analogs or these types of atmospheric circulation states. And that's a really interesting and important additional line of evidence. So one of the things we're working on at the moment is to include an assessment of the atmospheric circulation in our methods. And another aspect we're working on is similar to the tropical cyclones that Ben just showed, where we have really included different methods. Is we've also done a couple of or a few wildfire attribution studies, which is also very challenging, and you have lots of different variables that are important. So that's one area where we also try to identify what are the best methods, the best indices in what part of the world, and how can we combine lanes of evidence. And I think one other big field where we would really want to improve is on the vulnerability assessment, which at the moment is still is often a bit generic, and also it's hard to communicate because it doesn't have numbers, it doesn't have graphics. And so to have a more systematic assessment of vulnerability and exposure to be able to communicate that on par with the hazard assessment is another big step we want to make.
Thank you very much. I'm afraid we have arrived to the end of the event today. Let me thank you all for your attendance, and a special thanks to our two invited speakers today. Let me recall you that the next webinar is scheduled for the 21st May and will be about the AI assistant Ask WMO. This webinar will be delivered by Brigitte Perrin, Head of Communication of WMO. The exact title is Ask WMO, AI can help make weather, climate, and water information more accessible. And that's all. Thank you, and see you then at the next EMS webinar.